have for the end of the year seminars, we should have some incentives for people to tune in. Maybe we can announce for next year we'll have some prizes for this for the last seminar of the year. Those who participate will get some certificates and check maybe.
Or George, we can start sending them the T-shirts and mugs that we used to do before when Minlang and I hosted the seminar.
Yeah, we can redesign this to have pins, deponent, and hints together. The logo, we have the logo that you have in the YouTube video, maybe.
Yeah.
Is Oded logged in?
I see him. I'll email him.
Oh, there he is.
Hey everyone. Sorry, I had a bit of trouble joining you.
It's all right. Yeah, had it. So George, do you want to say something, or we can just...
No. I'll just make sure that we have at least one speaker.
Yeah. Okay. Hello everyone. Welcome to this week's croissant seminar. Due to the time zone and schedule conflicts, our second speaker cannot make it today, so we will have only one talk today, which is given by Oded Ovadia from Israel. Oded is currently a applied mathematics PhD student at Tel Aviv University. His field of study is application of deep learning to PDEs and numerical methods. He also works as a data scientist at Microsoft. And fun fact, I think I mentioned this before, that Oded started his bachelor at 12 and obtained his master at 17. So Oded, welcome back. And you may want to start the presentation.
Yeah, sure. Thank you so much. And thank you, Professor Kanendakis, for inviting me here. It's great to be here again. Right. So let me just, could you please share my screen? I think it's disabled. Yeah.
Oh, is it disabled? No, I think you can share. We give
right
access
now
to all the members of the seminar.
Sure.
Yeah.
All right. So can you see my screen?
Yes, perfect. Yeah, thank you.
So today I'll be giving a talk about a paper called the Transformer for Partial Differential Equations Operator Learning. Now, this paper was uploaded pretty recently to the archive. This is not my paper. I'm just giving an overview of the paper. And since it deals with transformers, and I've been playing around with transformers recently, Professor Kanendakis suggested that I give this talk, which I'm really happy. So let's start. First of all, the authors of this paper are mentioned here from Carnegie Mellon University. And again, this paper has not yet been published in a journal or a conference, but it has been uploaded to archive. So this is our agenda for today. We'll start with a pretty brief introduction about transformers in general and see why do we even care about transformers, why they're making such a big fuss in the deep learning world. And then we'll move on and take a deep dive into how transformers work, because this paper really deals with mechanisms that are inside the transformer architecture. So before we could understand how we use transformers for PDEs, we'll have to understand how transformers work. And then we'll move on to the paper itself. And finally, we'll see some results for PDEs. So for our introduction, what's a transformer? Transformers were originally proposed by Google Brain around 5-6 years ago. And it's essentially an encoder-decoder model that utilizes some mechanism called the attention mechanism. And the attention mechanism works like we expect attention to work in the human brain, where we want the model to pay more attention to certain aspects of the data or of a sample. And this mechanism was originally made for NLP in the original paper. And some famous examples that you've all probably met before are BERT and GPT. And for those of you who played around with ChatGPT or DALI or Stable Diffusion in the last couple of months, these are all involved with transformers. And this is the number of citations for the attention is all you need, the original paper by year. These are new citations. So we can see that this field really generated a lot of excitement in the deep learning and the data science community. Only last year, 2022, they had more than 25,000 citations, which is pretty ridiculous. Okay, so originally transformers were made for NLP, but in the last couple of years, people actually found out that transformers could be applied to other domains outside NLP. And the most famous example was the vision transformers in computer vision, where actually the transformers over there achieved state-of-the-art results compared to classic convolutional neural network, which was very surprising. So one question we might ask is if transformers could be used outside of NLP, could they be somehow utilized also in the domain of PDEs? So transformers have many advantages, and perhaps the most important one is their ability to capture long-term dependencies in data sets. And this makes them more robust than standard RNNs, which were basically the most common choice for dealing with such things, because RNNs have a very limited time window that they can look at, while a transformer can look at the sentence and find connection between the last word in a very, very long sentence and the first word, which is difficult for standard architectures. And also it's very computationally efficient compared to RNN. And one thing I really like about transformers is that they're often more explainable than standard CNNs or RNNs, because we can try and find out to which parts of the data the transformer paid more attention. And perhaps most importantly, they reach state-of-the-art results. So that's a reason to use them on their own. And finally, before we end the brief introduction, I just asked ChatGPT whether transformers can solve partial differential equations, and ChatGPT gave a really meaningful answer. And I really agree with the last paragraph over here, which is basically was part of my whole point in this talk, which overall using a transformer for PDEs is an active area of research, and there are many open questions and challenges. So yeah. And it is able to model long-range dependencies and handle complex relationships, which is basically what I said. So we can see that transformers are really impressive, and it makes sense to try and use them for the domain of the PDEs. Okay, now let's talk about how transformers actually work and understand the attention mechanism. So this very famous diagram over here, taken directly from the Attention is All You Need original paper, outlines the standard transformer model for NLP tasks. And already we can see that this is for NLP, since our inputs are embeddings, right, which is a very common NLP. But then let's try and look at each component over here, and then we'll take a deep dive into each one. So first of all, we said we have embeddings. We have something called a positional encoding. Then we have here two separate blocks, an encoder and a decoder. And within each one, we have something called a multi-head attention. And over here in the output, we can see that we have some sort of a linear projection and a softmax that yields output probabilities, since this is NLP. Let's briefly talk, or rather thoroughly talk, about the attention mechanism seen over here. We take the input of our feature space, and we use three different linear projections, Q, K, and V, which stand for queries, keys, and values. The queries and keys are projections of the same size, same dimension, dk, where V could be of any dimension we'd like, but often in practice, they're also dk. And the idea of the scale dot product attention, which is the attention that was proposed in the original paper in 2017, is to take the queries and the keys, multiply them, then scale them. Then in the context of NLP, we'll care about something called masking. We want to hide some words. In the context of PDEs, that doesn't really interest us, so we can just go ahead and skip it. And then we apply a softmax activation function to make sure that everything is inside a probability distribution between 0 and 1. And then finally, we take this result over here and multiply it by the input values. And here, mathematically, the attention mechanism for Q, K, and V, where they're all trainable matrices, is just I repeat again, a softmax of Q times K transpose over normalized by square dk, and then multiplied by V. And this is a demonstration, a fictitious demonstration. Here we have the sentence solving PDEs using AI. And this sentence could be transformed into such that each word is represented by a vector. This is called an embedding or a projection. So here we have 4 words where each word is a vector of size 8. That's our Q matrix. And then we have our K matrix, which is the same. This time it's transposed. And we have the columns representing words. But note that while we're representing the same sentence, we could and we hope to get 2 different representations because we trained the 2 projections at the same time. So we hope to get different embeddings and find some connections between them in the matrix multiplication. So over here, we get a square matrix, right? And we can look at the values of the square matrix. We get real values. But then we could notice something pretty interesting. We expect values that have some semantic similarity to one another or some connection to have higher values. So for example, solving and PDEs should be highly related to one another. And also, on the other hand, using an AI on the bottom right corner should be related to one another. But then perhaps other connections, for example, solving and AI shouldn't really be related to one another, so we expect them to get lower values. And this is exactly the heart of the attention mechanism. We want the model to pay more attention to some aspects of the data. So that's what we're seeing here. But then in the classical attention mechanism, we mentioned that in NLP, we care about probabilities. So we need to take a softmax of it all, just to move it all to numbers between 0 and 1. And the scaling over here also prevents the model from exploding. So we know that the softmax probably isn't that relevant for machine learning applications in PDEs, but we'll see that the scaling is still something that is necessary. And finally, once we have that attention matrix over here, the square one, we could multiply it by the values. If you recall, we have the queries, the keys, and the values. So first of all, the left-hand matrix is calculated using the queries and the keys. And then finally, everything else is multiplied by the values. So we expect the left matrix to put some weights on the values matrix and nudge them toward the right direction in terms of attention. And everything we talked about so far dealt with one attention head. That's how it's called. But in real application, we don't really care about one attention head. Usually, we want to do something called a multi-head attention and use multiple attention heads at the same time. So here we have a definition for multi-head attention of Q, K, and V, where each attention head, the ith attention head out of H, is defined as an attention, a single attention head, of the original matrices multiplied by, projected by other linear projections W's. So note here that the Q, K, and V are trainable weights, and they're also multiplied by other trainable weights. And then we'll repeat this process and finally concatenate all of the heads together and use another projection. And I think it's probably easier to understand it using this diagram. We have V, K, and Q, which are the same. They don't change, but they're projected using different linear projection into scale dot product attention, which are finally concatenated and then being projected again. And the idea of multi-head attention versus a single head attention is that we want our model to pay attention to more stuff at once. So if we take an image processing example, maybe we want one attention head to pay more attention to edges or vertices in the image, but we would like another attention head to pay more attention to stuff that happens in the background of the image, or lower frequencies, higher frequencies, and so on. And another important concept to understand is cross attention. And cross attention is slightly different from what we've seen up to far, but not that much. Because what we've seen so far is self-attention. Q, K, and V are all trained using the same feature space H. But then if we'd like to calculate a cross attention, we can take Q from one feature space and K and V from another altogether different feature space, and then calculate their attention together. And we get some really good advantages when we use cross attention compared to self attention, because it allows us to combine different inputs. So we can learn simultaneously the attention between multiple things at once. And then also one added advantage is the fact that we can also try some multimodality stuff. So for example, Q can come from a text origins, while K and V can come from, say, image processing. And this is extremely useful. And we can also start to think how this could be useful for PDE applications. And another very smart idea they came up with was positional encoding. And one of the problems that the attention mechanism has on its own is that attention has no particular order. And so we need to tell the attention mechanism what's the order of things. So the way they solved this difficulty was by applying positional encoding or embedding, that they add a relative location information for each and every word. In this case, location and pause position means where the word is located within a sentence. So we tell the model that say a word appears at a certain index within the sentence. So that's really important. And they actually found that, that they could use simple sines and cosines to represent it without any learning at all, which is a very nice result. Okay, so now that we basically know how transformers operate, we can move on and talk about transformers for partial differential equations operator learning, which is the title of the talk I'm giving here. Let's take a sneak peek into the algorithm itself, because we're going to delve even deeper into the attention mechanism. So what we have here in the paper is an input function plus some grid points, which are then being transferred into some transformer encoder. Then we have a completely separate set of grid points, which are being encoded using another transformer encoder. And at a later point, an attention mechanism is applied between the two encodings, which is then decoded into some output function. And already by looking at this sneak peek of what's to come, I think perhaps you can notice a certain similarity to deep on X, right? Because we have something that looks here like two inputs with two grids. So that's where we are heading, and we'll talk about it more soon. But to understand the mechanism, as we said, probably softmax isn't really the way to go in PDEs, since interpreting the idea of probability within strictly physical PDEs is not that intuitive. So what they used is attention without softmax, which is actually, they cite a paper from Cal, from I think University of Missouri, who actually gave a talk in this seminar in the last year. And there we talked about two different interpretations of the attention without softmax in the case of operator learning. So we can look at this formulation of the standard scale dot product attention right here, where Z is the output. We have a weighted sum where alpha ij are the weights, and we have Vj here as the values from the values matrix, where each alpha ij, just over here, this is the softmax, according to some weighting function h. Then what happens if we choose to completely remove and ignore the softmax? That's one question. And what other choice of h can we pick to make the problem, to adapt the problem to the domain of PDEs? So Cal suggested two alternatives titled Fourier type attention and also Galerkin type attention, which the authors of this new paper cited and relied upon pretty heavily. So we'll talk about that a bit more, even though it's slightly outside the scope of this paper, but it's important to understand the type of attention that is being used. Okay, so we'll start with the Fourier type attention. This is a row-wise interpretation of the attention mechanism. I know the notation here can be slightly confusing. Subscript means rows, and the superscript means columns. So over here, we're looking at the jth element of the ith row. We can view it as a simple weighted sum, as we talked about. But if we were to choose H, the weighting sum, to be just 1 over n, like equispace points in space, we can see that this over here could be viewed as a numerical quadrature for some integral over some domain omega, where the domain omega is being discretized by values xi. And then this all happens according to some kernel function k, where Vj are the corresponding basis functions in the new generated function space. So that's why Carroll called it Fourier attention type, because it resembles Fourier, and it's basically an integral transform. And he also mentioned a different type of attention, which is a Galerkin attention. This time we're viewing things column-wise instead of rows. So we take the ith element of the jth column. Once again, just basically the same thing, only we move to column notation, so we get this inner product. And so he claims that this could be viewed as an inner function. Sorry, it's an inner product over here, where the dot product can just switch to an inner product for functions, where functions approximate, or rather the columns here discretize these functions on this defined domain. So in the end, what we get over here is pretty similar, only that the ith element of the jth column could be viewed as follows using integrals. And then he showed the two different ways to look at the Fourier and Galerkin attention within the context of classical attention and transformers. So first of all, the Fourier type transformer, it is scaled by n. Then we take Q times K transpose times V as usual. But the Galerkin transformer is the Galerkin type attention, sorry, is a bit different. First of all, we compute the product between the K's and the V's, and only then move on to Q. And you'll also notice the hat notation over here above these functions. Now, this denotes column-wise normalization operation on the matrices. And you'll also notice that it's different between the two cases. And it actually makes sense, because when we think about it, in the original transformer paper, only everything inside the transformer, so inside the softmax, is being normalized. So essentially, when we're moving everything and removing the softmax, it makes sense just to normalize everything that is related to the dot product. So that's what we have over here. Now, for operator learning. Now, this is the crunch group. So obviously, there's no reason to discuss and say what operator learning means to you. You obviously know about it, but it is important just to talk about the notation so we could understand everything that is going on in this paper. Well, they talked about an operator, G theta, where theta are the parameters of choice in their architecture, that maps values from function space A to function space U. And now in terms of annotations of discretization, they denoted by dx the x discretization of the domain A, and by dy another separate discretization relating to the range U. And then samples are from operators. And finally, they used relative L2 loss in their architecture over here. I guess they added something like an epsilon over here for stability. They didn't write anything about it, but otherwise I suppose it wouldn't really work. But so far, pretty standard operator learning formulation. Now for the cross-attention part. I said earlier that we'll come back to cross-attention and think about how it pertains to PDEs. So here it's a pretty interesting concept, because in self-attention, Q, K, and V are all different linear projections, but they come from the same input feature space. But in the setting of operator learning, it doesn't really make sense, because if we were to use only self-attention, we'd look only at the domain of the operator, which isn't that interesting. But then when we look both at the domain and the rate simultaneously, then we could hope to find some mapping between them. So cross-attention over here is just taking the keys and the values from the domain and taking the queries from the range, and then calculating the attention between them. And I promised to talk about a relation to DeepNet. Unfortunately, they didn't really elaborate on it in their paper. I think there's a lot to be said over there and a lot for them to explain, but they did mention it, which was pretty interesting to see in this formulation. They can view the cross-attention as follows, like this. So we have this sum over here times this set of functions, where KL, VJ, and QL are all outputs that come from a neural network because they are trainable, if you recall. So essentially, on the left-hand side, we have the branch, and on the right-hand side, we have the trunk. And as I said, they didn't really elaborate on the connection to DeepNet. So my best interpretation was that they used DeepNet as a type of the feature extractor for that for their problem, and then continued to use it as an input to a feed for neural network. So we'll see some results about how that works. In terms of transformer inputs, well, the three main inputs to the transformer, or rather to the encoder of the transformer, if we recall, this is the first part of the transformer. First of all, we have the sampling coordinates xi. We have the sampling of the function a at these specific points, and also the query coordinates at the range of the operator yj. And in terms of positional embedding, they didn't use the standard signs that appeared in the original attention paper, but they use a slightly different version called rope or rotary positional encoding, where the encoding is done using Euler rotation matrices. And they find that it was pretty useful since they're solving a grid problem. And by using this on a grid, they have the useful property that the product of two values in the positional encoding could be actually translated to something that is related to distance between points. So that makes a lot of sense for the settings, the setting of PDEs, even though this positional embedding was invented originally also for NLP. And this is the encoder itself.
Oded, why they chose this positional encoding for the? Is there a particular reason? If you go back one.
My best answer is the ablation study. They tried different kinds of encoding. They tried also learned encoding and find that actually these positional encodings were pretty good and outperformed the rest.
So this capital theta was the diagonal of the R matrices, right? Can you go back?
Yeah, sure.
Slide, please. Yeah.
Sure. Yeah.
So that's the rotational matrix.
Mm-hmm.
And do they explain? Is there any rationale why they chose the rotational matrix, for example? Is that to have rotational invariance or something?
And they didn't really mention it, but they tried different things, and this one worked the best. And I was actually surprised to see that it works well in NLP, because in PDEs we could try and find something that is related to rotations, but I can't think of any interpretation for sentences and words in terms of rotation, right?
Okay, fine. Thanks.
Sure. Okay, so this is the encoder itself. So as we said, we have two sets of inputs. First of all, the observations of the input functions, where we have the coordinates themselves and the functions at these coordinates, which are propagated forward using a block of MLPs. And using these MLPs, we get an input encoding. Now, this is not exactly the same as an embedding, but this is one way to get an input encoding from a set of points. And then this is propagated forward in the network into a block of self-attention, which is repeated L times. So here, each time we take the input encodings, then we calculate the linear projections, put them inside the attention, and then another layer of MLPs, and so on L times. And then we only use two projections outside for pretty obvious reasons we'll see right now. The second set of inputs is just the sets of the coordinates of the query locations. And we do the same thing. We project them into an encoding using the queries, and then use linear encodings to get the queries. And now that we have one projection, the queries from here, and we have the keys and the values from the self-attention block, we can calculate the cross-attention between them. And this is the part that really makes this architecture feasible in terms of learning operator mapping, because otherwise it couldn't really connect the two of them. And then it is being transferred into another layer of MLPs, which brings us latent encoding of the query locations. So this is a bit different from the original transformer architecture, right? Because in the original transformer, we had two separate sets of inputs that connected together inside the decoder. Here, this happens already inside the encoder itself. So once again, we get three separate inputs, and our final output of the encoder is just a latent encoding.
So Oded, here they have two encoders only. One encoder for the branch, one encoder for the trunk, basically.
Yeah, that's right.
And they, in addition to changing the attention mechanism with the softmax and so on, they still use the multi-head, right?
Yes, they do. They do. Sometimes they do, sometimes they don't, in different experiments.
Okay. And the masked is the decoder, so there's no issue about the masked.
Right. They're not masking anything.
Okay.
Yeah, usually in the setting of NLP, we want to say mask words that appear in the future because we want them only to look back or something like that, which we don't want that for PDEs.
And in this schematic, you don't show the cross attention, which is basically the inner product of Woodtake, right?
Right over here.
That's there? Okay.
Yeah, that's a cross attention. That's a self attention over here. And this over here between the blue Qs and the red K and Vs, because they come from different areas, this is the cross attention.
And why do they need, after the cross attention, why do they need this extra layer of MLPs?
Well, that's basically how a transformer block looks like. So because they did the same thing over here, right? An attention followed by an MLP, so they just kept it the same.
Okay. All right, got it. Thank you.
Wait, Oded?
Yeah.
Hi, just a quick clarification question. This is Leonard from Crunch Group.
Sure.
So in the top half, so the linear projections, the QKV. So what they're saying is they just for the extra KV linear projections, they just use those. So say you project into 10 different QKV linear projections. So for example, 8 of them would be used in the self-attention, for instance, and 2 of them would be used for the cross attention in the trunk and attention. Is that?
Not exactly. What happens over here is say you say we have 8 over here, right? And then we have completely separate projections over here. So they're not really related to one another.
Okay, but they're all linear projection matrices for the put encoding of the branch net.
Yeah, that's fine.
Gotcha. Okay, thank you.
Sure.
Oded, sorry, one more question. Here the domains are spatial domains, right? There's no time advancement, or
you'll see it in 2 more slides. There are 2 variations. For
right. So here we assume static. Not time advancement.
Right. The time advancement happens inside the decoder.
Okay. Yep.
Yeah. So now we can talk about this slightly more formally in terms of the architecture itself and what happens inside the attention block. So as we said, we have 2 different encoders that basically merge into one encoder, where we have L self-attention blocks in the first one. So we can look at it like something like this. Each attention block is being composed of feed-forward neural network, which in their case they use the MLPs, also in the standard transformer architecture. And then there's also a skip connection over here, like in the ResNet or residual mechanism. And it makes a lot of sense to combine ResNets and attention, because usually transformers, or sometimes they can be extremely deep. And when we're using extremely deep architectures, adding residual connections is always a good idea. So here they're being normalized using layer norm. And then the output of the previous one is, once again, just the attention mechanism. So just to kickstart it, they use F0 as the output of the standard MLP, which is the basic encoding we've seen earlier. And for the query locations, there is no self-attention, only a feed-forward neural network. And they mentioned the first layer they used was the random Fourier projections that they tried with and without it, and finally by initializing it that way, it was more useful. Now the cross attention is computed between both of them, where finally it is being followed by a feed-forward neural network. That's how we get an encoding. And once we get an encoding, we want to talk about decoding, obviously. So this is what Professor Kanidakis asked. In the case of a steady-state system, this is very simple, right? If we have no time dependence, we can just take the latent encoding and use a simple MLP decoder to find the actual values of the function. That's very simple. In the case of a time-dependent problem, that's a bit different. That's a bit trickier, because we need to do some sort of propagation. So what they propose over here, which I've seen in other papers as well, is propagating the solution of the PDE in time in the latent space. So here they have the encoding, and they use an MLP to propagate it forward. So say if we have 50 time steps in the domain, they'll make 50 time steps here in the latent domain using the encoding. And it's important to note that the MLPs here are shared. So as I said, if we have 50 time steps, it doesn't mean that we have 50 separate blocks of weights that train separately, because that would be prohibitively expensive. They just use the same MLP block 50 times. And then the decoding, you just, once again, a simple MLP at each time step. So that's how the decoding is done. All right, so let's talk about, yeah.
Hi, Oded. This
Yeah.
is Jin from Crunch Group. Can I ask a question about the previous slide?
Yeah, sure.
Yeah, so I'm actually curious about, for this time-dependent system, does your input observation also changes with respect to time, or it doesn't change?
It depends on the problem. Yeah, in some problems they use the Navier-Stokes equations, which obviously they change over time. So yes.
Yeah, so I'm wondering, like, if your input observation changes over time, how does that come into your transformer architecture? Because here it seems like you see in the middle, the latent encoding only depends on the encoding in the first time step. Basically, maybe I understand it incorrectly, but it seems like you put a neural network on the latent encoding for the first time step to get the latent encoding in the second time step, but that doesn't take the information from the input observation at the second time step. Maybe I missed something here. Did I make sense?
Well, if you're talking about fusing the information, then it's important to know that the encoder and decoder are trained together. So during back propagation, there is information that coming from the query locations themselves inside here. If that answers your question. Or maybe wait, are you talking about changing of the query locations themselves between time steps?
No, I'm talking about like let's say, for example, if you have some equation like simple equation like u prime t equals to ft, and ft, basically I'm saying ft is changing with respect to time, and how does that changing f like goes into this transformer? I mean, just like in a very simple case, like so so like if I understand it correctly, since f will be changing with respect to time, then then you will input them into different you will input them into encoders to get different Latin encodings. But here seems that the MLP, because you have this MLP, you only input the FT at the first time step to get the encoding at the second time step. But I'm not sure, but maybe let's not waste too much time here. Maybe I can ask you after the session, if that makes more sense.
Yeah, sure. But that's a great point. If you have like a time dependent, say, source of the wave equation, I don't know how they would deal with that. Yeah, that's a valid point.
Thanks.
Sure. So let's move on to discuss results. In terms of evaluation, the authors compare their approach to the original Galerkin and Fourier transformers that were proposed by Cow, which I mentioned earlier. Then they compare themselves to FNOs. And here I have something really important to say about it. It looks like the way they thought about this problem was that they've seen the FNO papers, and then they tried to replicate a lot of stuff from there, but not so much about DeepNets. And we know that FNOs are a special case of DeepNets. So it's a bit unfortunate that they just limited themselves to specific types of DeepNets and didn't allow themselves to try more, say, more exhaustive search of architecture that the more general DeepNet allows us to do. Well, you'll see my point pretty soon. But okay, so they also use the multi-wavelet based operator and the graph neural network, GNN. So these are the problems they tested on an equispaced grid and the non-uniform grid. We'll talk about each one of them in detail. And also the choice of hyperparameters. Obviously, we're not going to go over everything in here, but it is, Professor Kamiakis, I think you asked this. Here in the encoding, they used only one single attention head for the Burgers and the Navier-Stokes, but then in the decoder, in the query encoder, they used more attention heads. And finally, the most important stuff for us to look at is the total number of parameters, which is not huge, right? But it isn't that small too. So let's start with the 1D Burgers equation. Here, their goal was to learn the mapping between the initial condition and the solution at time 1. So here is their table of comparison. They compared themselves to FNO and FNO with the Galileo activation. And here FT stands for the Fourier transformer. And we can see over here that the results are not that good compared to the FNOs and the Fourier transformer. And I find it a bit odd that when increasing the resolution over here, the results actually slightly deteriorated, even though it's a relative LT norm, which was a bit odd. But then we can see that the Alformer still beats the regular FNO and the multi-wavelet. And here we can see some results, which using the eyeball norm, they look pretty nice. But I noticed over here that something that might be missing is the addition of shocks, because the further we propagate the Burgers equation, we get closer to shocks. And we can see over here, we're getting pretty closer, but not that close. And we know that the FNOs fail when they're using, when they see some shocks. And so it would be interesting to see if the transformers also suffer the same problem. So I didn't get an answer to that question. But then they tried another problem, which was a 2D Darcy flow, which is not time dependent. And they tried to learn a mapping between AX and FX. And over here, still, Alformer wasn't really that competitive compared to FNOs and the Galerkin transformers. Even though we have to take into account that these errors are really low. And once again, when we look at it, we can barely see the difference between the predictions and the ground truth for different types of problem. So our results are pretty good and maybe still not competitive with the other approaches they've shown. But then here for the Navier-Stokes equation, which was a 2D plus a temporal one, here results were much better. And you can see over here, their goal was to learn a mapping between the times 0 and 10 and a grid, which is from the square from 0 and 1 to some time after 10. And they generated 5 different tests, changing the values of nu and t accordingly in each test, where they also looked at NS2 part, stands for partial, and NS2 full, which means whether we're looking at the full data set or some smaller part of the data set. And I think this was a very, very interesting result, because we see that when they're using the full data set, actually the Overformer beats all other methods. But then when they're only taking a small part of the data, then the transformer is not so good compared to other methods. And this is really interesting because of how transformers, well, of what we know about transformers. Generally, those trade-off with transformers. Unlike standard CNN, there's a common saying that transformers tend to saturate a bit slower. So by adding more and more data, transformers keep learning and not really saturating that much. But then on the other hand of this trade-off, you still need a pretty significant amount of data to get good initial results. So that would be my theory on what we're seeing over here. So also in the NS mix case over here, where they used different nu values, they also used a larger data set than the NS1 and NS2. And once again, the Overformer was pretty competitive. So one thing, one conclusion we can find from these experiments is that probably transformers need quite a lot of data, even in the setting of PDE. So here, quite a lot means around 10,000 samples. So it's not that a lot. And here are some results for different Reynolds numbers and different times. And we can say the results look pretty good. Here's for Reynolds number of 20. Here's for 200, and here's for 2000. Now, we know already about DeepNets that they were capable and pretty successful in the setting of high-speed flows and even hypersonics with huge, enormous Reynolds numbers. And it would be interesting to see how transformers behave in such settings, which are obviously very difficult and more difficult than this. But this looks quite promising. And also they used some problems on irregular grids. So for example, at the croissant equation, they used a boundary value problem. And when they have the information about the boundary and they try to predict the interior. And they compare themselves here to Overformer and GNN. And now they said that they couldn't compare themselves to FNO, which is okay, it may make sense. But using irregular grids is possible with certain types of DeepNets, as we've seen before in your group and in your papers. So once again, it's a shame that they compare themselves to a more general form of DeepNets. But still, the results look pretty cool over here. And we can say that without any data augmentation, they actually beat the GNNs they trained, which is pretty nice. And also in terms of data set size influence, this is really strengthens the point of why we've seen such different results for different data sets. We're talking about transformers. So when you add more data, results keep improving. And I wish that they could keep the trained data amount scale even further, because I'm really curious to see at which point the transformer would saturate and stop improving, because it's not that intuitive. And here they also compared the different types of attention and normalization they had. So in the case of, for example, in the left-hand side, we have the Burger's equation, sorry, the Navier-Stokes equation. And in the case of Navier-Stokes, Galerkin outperformed Fourier, while in the case of Burger's, Fourier outperformed the Galerkin one, which is pretty interesting. And also they find out that layer normalization, sorry, instance normalization was more successful here in this case than the full layer normalization. where instance normalization is pretty similar to batch normalization. They also tested the effect of the scaling and the initialization method, because as we've said, we can discard the softmax activation because we don't really need a probabilistic output. So they said, why not? Let's try and discard the scaling. And as they show, this is not a good idea. When you drop the scaling, everything just explodes upwards in terms of the error. And it makes sense because when you have a network that has residual connections, you do want to scale everything and tone everything down, so values wouldn't get exponentially high. And also in terms of initialization, they found that Zaber and orthogonal initializations are pretty similar to one another in terms of error. And in terms of computational cost over here, they looked at the number of iterations per second and the number in the memory footprint and the number of parameters of the different methods. And we can see that the old former is pretty efficient, especially compared to FNO, and FNO2D and FNO3D, which are very hard to scale. They also tested the influence of the positional embedding. As I said earlier, they tried different embeddings and compared the positional embeddings to see which encoding would give them the best results. And we can see the results with the rotary positional encoding and without it. And on the left-hand side, I can't really see the difference, but on the right-hand side, when they plot the error maps, suddenly it becomes way clearer that using the rotary positional embedding was pretty useful and vastly reduced the error. And it makes sense because otherwise the attention wouldn't really know anything about the allocations.
Excuse me, this is Lulu. So I think the reason they use the sine cosine positional encoding is for all these examples, they are mainly periodic, right? For periodic, we know if we use cosine sine input features of positional encoding, they usually help.
Mm-hmm.
Yeah, that's my thought.
Yeah. It makes a lot of sense. Yeah, I agree.
Oded, do you have the results for the Airfoil? Because the Airfoil results are not periodic and they don't look good.
Yes, so actually the Airfoil results are the only ones I didn't show because in the Airfoil results, they didn't compare the methods to any other method. So
right.
there wasn't.
They only show with the naked eye norm.
Yeah, exactly.
Naked eye norm to show that, and even in my old eyes, it didn't look good. So that may be that may support Lulu's observation.
Yeah, that's a great point.
There's a last example of the Airfoil that they have and they don't have L2 errors. They don't have any of that.
Exactly. Yeah, they didn't have any table or anything I could actually show and make a concrete claim about. Yeah. So and now for something that is actually pretty cool. As I said earlier in the talk, one thing I really love about transformers is that transformers could be a bit more easy to interpret than other types of networks. So they've done something pretty interesting over here. They took the training encoder they had and calculated the encodings of the datasets, where the datasets was composed of samples of Navier-Stokes with different viscosity values. And then they used the encodings, and if you recall, the encodings are just vectors. So what we have here is essentially a table, which means we can calculate the principal component analysis. So we can calculate principal components, and then took the two largest PCs and projected into a two-dimensional grid. And it's something I think this is pretty cool that we see that values with similar viscosities tend to be clusters around one another. So on the left-hand side, we can see slightly higher viscosities, while on the right-hand side, we can see lower ones. And this essentially means that their encoding actually learned something meaningful, which is pretty interesting. And another thing they've done is take the testing samples and use the encoder, and also before they're taking the training samples and trying to learn a mapping between the encoding and the original viscosity. So they used a simple linear regression model to train the mapping between the encoded values and the viscosity. And we can see in the test set over here that actually a simple linear regression was able to reconstruct the new values pretty well, or actually amazingly well. So that also means that the encoding learned something about the PDE itself. It learned parameters related to the viscosity. So some final conclusions. We've seen that transformers can be applied to PDE operator learning. And we saw that there exists a modified attention mechanism without softmax that could be also applied to PDEs, but it's still very much a nascent domain. There is a lot of work that remains to be done here. As ChatGPT so wisely said, first of all, I would like to see some comparisons to general deep nets. I would love to see some results on larger data sets, because we saw that once they increased data sets, results looked way more impressive. And then some more about explainability would be very nice. For example, seeing how the attention mechanism itself looks like. Looking at the attention matrices in terms of PDEs is not that standard and could actually give us a lot of insights about what the transformer actually learned. So many open questions and many research opportunities. And on that positive note, thank you very much.
Thank you, Oded.
Yeah, sure. Do you have any questions?
Let's see. Do we have any questions for our speaker?
Well, maybe we can revisit Jen Zhang's question on if you have, let's say, time-dependent boundary conditions or time-dependent right-hand side that you map to the solution. Do you have to modify the architecture? I think, Jen, that's what you were asking, right?
Yeah, sure. I think over here, when we have the time-dependent system, my approach, my instinct tells me that you'll have to add something into these outputs over here, right, at each time step. We'll have to add some additional information.
Okay.
Yeah.
And then for the time advancement, can they take? Have they looked at different time steps?
Not that I've seen. They said we tried different architectures of the shared propagator. They tried switching to convolutions, and they found that MLPs work better. But changing the delta of the time would be very interesting.
I wonder if they can beat the CFL number, for example, in an advection equation or something.
Yeah, that's interesting.
Yeah.
Because then you don't just save time on the forward propagation, you also can move to a smaller latent domain. Yeah. So you also propagate on a smaller domain and for fewer time steps. Yeah, that would be really interesting.
Yeah.
Do we have more questions?
Oded, have you seen any literature on transformers for segmentation also, since you were looking at different beyond NLP, since you mentioned so far this is from Amir is one of the first, probably the first, and your work, of course, on VIT, right? But you haven't published it yet, so
yeah.
So it's the first on PDEs, but there are works on transformers for segmentation also, because Juan Toscano here is trying to look into it. What other domains transformers have been used at?
Well, you're asking about semantic segmentation?
Yeah, for example, segmentation, or what other domains?
Yeah, segmentation is actually a really good example, because most modern semantic segmentations architectures use a backbone of some architectures. So, for example, you have something like a DeepLab V3+. It takes a backbone, say, ResNet 50 or an exception network or what have you. And then instead of this pre-trained backbone, you could just put a vision transformer inside it, or just switching the backbone. So that's one approach for semantic segmentation that actually, I think it achieved basically state-of-the-art results compared to other methods on the, I think it was the Pascal VOC dataset. So these are very good results. And I know transformers have been applied also to time series, which is very interesting and I'd say a bit more expected than images. Right, because you have sentences are basically time series, right?
Yeah, we have seen a paper, I think, from IBM on financial data. Alan, I don't know if Alan is he was attending before, right? And he's looking into that actually right now.
Yeah. This is basically a period of time in the deep learning community when everyone is trying to apply transformers to everything because they've been so successful, even when moving to other domains. So yeah.
Hi, hello. My name is Juan. I'm working with the segmentation model that Professor George mentioned. You said that for this case we do not use like the backbone when we use a vision transformer instead of that. That's what I understood. And you said something. And you said something about a library or something like that. So can you repeat that, please?
I'm not sure if there's a specific library. Everything that is related to transformers you can find on Hugging Face, which is pretty simple. It's mostly in PyTorch. And then you also have some materials on Google themselves. You can go to their GitHub and look at DeepLab v3+. DeepLab is basically just an architecture where you can insert your own backbone. So you can also look at swing transformers as well, SWIN, which are very useful for segmentation.
Okay, thank you so much. So in general, it's Hugging Face, DeepLab, and the Google documentation itself, right?
Yeah, and the swing transformers. Yeah. Swing
transformers. Thank you so much.
Sure.
I have a comment on the last question. Another resource for transformers. On GitHub, there's a user. His ID is Lucid Rains. LUCIDRAINS, so Lucid Rains. He does a ton of open source implementation, mostly in PyTorch, about modern transformer architectures that appear in the research. So it's a good repo to check out.
Leonard, can you put it on the chat? Can you put the on the chat, please?
Yeah.
Thank you, Leonard.
Strange, yeah.
All right. Thank you, Oded, for your presentation. And George, do you want to say anything before we close the session?
No, I just want to thank you, Zogren, and some data for creating the YouTube channel. I think that I see now hundreds of views of every one of these talks. I think we had like 600 or more views of the talks, and in such a short time. So I think that was a great idea. Everyone who attends here should encourage their friends and family to subscribe so that we can go over 1,000 subscriptions. So then we can also have a free Friday lunch. But definitely the contribution of some data and Zogren week in and week out to educate us, I really appreciate that. And so also we want to say that we'll start the new year with a bang. Some data. Do you want to tell us who's giving the next talk?
So we are going to start so on the 6th of January, we are going to start the new year. Our first presentation would be from a very famous person, and he would be joining our, he would be giving this with one of his students, and probably we all know him. Just let me tell you both their names. Just give me 1 second. So his student is Alexander Duval, and he would be accompanied by a very famous person, Yoshua Bengio.
So Bengio is the next speaker.
Along with the student.
The next speaker, yeah, next speaker and his student.
Alexander Duval.
Yeah, Alexander, yeah. So please find interesting papers. It will be nice for the next year. We had Oded also given 2 talks. Other people have not given any talks, papers to present for the benefit of all. And with that, I want to wish everyone Happy New Year, and thanks everybody for your contributions this year.
Happy New Year, guys.
Happy
See you
New
next
Thank you
year.
very much. Say Happy New Year.
Yeah. Bye.